Welcome to the first lesson of this introductory course on quantum optics. In this lesson, you will discover how it is possible to quantize the electromagnetic field starting from classical Maxwell's equations and using a method known as canonical quantization. We will consider today the case where the field is far from the sources, that is to say, free radiation. Moreover, we will effect the quantization for a single mode, leaving the multimode case for a future lesson. Even for a single mode, the canonical quantization of the electromagnetic field is not simple, but if you make the effort to follow me, you will be rewarded. You will know where the formalism that we will use all along the course comes from. When I started reading quantum optics papers, I had to accept that formalism without justification, and I was frustrated until the moment when I found the presentation of the reasoning leading to the equations that we use all the time in quantum optics. I would like to avoid that frustration to those of you who, like me, want to know where the formalism comes from. I know that not everybody is the same, and you may be mostly interested in learning how the formalism works in order to apply it to the wonders of quantum optics. Even if it is your case, do not skip this lesson, since we will introduce many notions that will be very important in the rest of the course. Let us look together at the summary of the lesson, and I will tell you what you might skip. In the first section, I will explain the general method to quantize any classical system. You may decide to skip this. In the second section, you will first apply the general method to the quantization of a classical mechanical harmonic oscillator. You may want to skip the beginning of that part, but as soon as you hear of Dirac formalism, it is time to listen carefully, since Dirac formalism is used all the time in quantum optics. After a pause, we will continue our survey of the quantization of a mechanical harmonic oscillator. It will allow me to introduce many notions that will be useful for the whole course. In particular, do not miss the explanations about energy levels, number states, quantum fluctuations. In section 3, you will find the definition of a classical mode of radiation, a notion essential in quantum optics. In section 4, you will discover that radiation in a classical mode can be quantized exactly as a classical harmonic oscillator. This will allow us to jump directly into the full formalism of quantum optics. As usual in quantum mechanics, we must define the quantum observables associated with measurable quantities. This will be done in section 5. In section 6, you will discover how the properties of the eigenstates of the Hamiltonian allow us to define the notion of photon, one of the landmarks of quantum optics. Another important consequence of quantization is the existence of vacuum fluctuations. Fluctuations of the vacuum may be an oxymoron in the classical world, but it is a fact in quantum physics with important consequences, which can be observed. This first lesson, I must admit, is a little too long. However, it would have been frustrating to split it in two parts, since the exciting matter is in the second part. But do not panic. Future lessons will be shorter. And now, embark with me into quantization of radiation.